Hello students, in the previous lecture of carbohydrate we have studied about the classification of carbohydrate, and in this lecture we are going to study about the depiction of the conformation of open chain carbohydrates. So in this case what we have to do, we have to take one example. That is, example is you can take this aldehyde. This is the structure of aldehyde, or you can say it is a D-glyceraldehyde. Why it is D-glyceraldehyde? Everybody knew it. Then also once again I will tell this, because this hydroxy group is on right hand side, so that it is a D-glyceraldehyde. So if you take, or the other way also we can write this D-glyceraldehyde by like this. Here is CHO, here is OH, here is hydrogen, and here is a CH2. So what is there? What is important? If you, this is the possibility to rotate both sides. If you rotate to right hand side, and what happens if you rotate to left hand side? So if you rotate to right hand side, this what? This carbon is putting on the plane only. What happens if this hydroxy goes back, this CHO, and this is the CH2. So this is the same. Okay, don't get confused. These both are the structures same. Further, if you again rotate, what happens? This again CHO, yes, and here is OH comes this side. Here will become this CHO, and here is a CH2, and this OH again outside. Right? Or the other way of representation is, you can put this one, here is the CHO, here is the CH2OH, and here again OH. This way also. Then the other way is, here is a CH2OH, here is a CHO, and this OH. This, what we are doing here, we are rotating this hydroxy. See, this structure is rotating clockwise, this rotating clockwise, and this rotating to the clockwise. And the last one possibility is that, yes, this CHO is here, and this CH2OH, and here OH. Okay, this is about when we rotate glyceraldehyde in right hand direction. Now we will see what happens if you move to the left hand side, that we are going to study this. Okay, so this is about the right hand side. Now we move to the left hand side. What will happen? Just the difference in that, see, this is a CHO and this is a CH2OH, right? This OH comes as such above. See this one first structure, then the second structure, this OH remains as such over here. Here is a CHO and here CH2OH. This is the depiction of the conformation of open chain. Okay. Now the third structure will be, okay. So here is a CHO, CH2OH, and here OH. And see this OH, just a rotation of this one through the left hand side. This left hand side, this left hand side, this left hand side. If you rotate, these are the depiction about the diglyceride. So if it has only one chiral center. This carbon is a chiral carbon, but it is a only one carbon center, chiral carbon center. So what will happen if you take the example of D-erythrols? In the D-erythrols, there are two chiral carbons. You know, in the erythrols there are two chiral carbons. So the structure can be written like this: CHO, CHOH this side again OH, and here CH2. Right? The structure, this is the structure. If you write another way also, this is a CHO, then here is a CH2OH, OH, OH here, H, or you can write this also like this. Okay? If you take these two, these are similar structure, don't get confused. These two are the similar structure. What you do, another way of representation is different. For this one, this is a CHO, and here is a CH2OH. Here is a CH2OH. These two hydroxy groups on the same side. What does it mean? This should be on the same side or same plane. Or this is equivalent to what this structure can be written in other way also. If you take this CH2OH, just make the opposite this one, but both are in a same plane. This is the same. Okay. Is there any other way of representation for this? Yes, there is a other way of representation. What you have to do? This carbon is in a bending position. Yes. But if you want to make it a zigzag-like carbon structure to maintain the bond angle, what you have to do? We have to write CHO here, this. Then here CH2. Okay. Then CHO and CH2OH is there. This carbon is having a hydroxy group. We are putting the same. This carbon, if it is on this side, it is above the plane. But whenever it goes this side, this is the below the plane. So this is the representation. And for this structure also can be written in other way. Here is a CHO. So we are going to write the zigzag structure. Right? Here is a CH2OH. This OH you keep as such. Then this OH becomes above the plane. So this is the Fischer projection and the conformation of D-erythrols. These are the Fischer projection and conformation of what? D-erythrols. Okay, this is the conformation and the depiction of the D-erythrols. Now, if you go, what will be the case in case of D-erythrols? This is a D-erythrols. Then we are going to D-threos. So what will be the case that we are going to study here? This is about D-erythrols. write down the D3O structure if you know. If you don't know, we'll write here. The D3O structure is written CHO. Only the difference what? Here is H, OH here, COH here, H this side and CH2OH. Yes, what is there? D means this hydroxy group always on the right hand side. Okay. D, erythro, in case of erythro, there was a OH, but triose, it is a OH on the left hand side. This is the D triose, PHREO, SED triose. The same way, the same structure can be written like this also. How can we written? CHO, CH2OH. This hydroxy, if you write above, then this hydroxy goes behind. Okay. So similar way, this is the way of one representation. This structure also can be written this way also. See, here is CHO, C, carbon, carbon, and here CH2OH. Here is OH, H, OH, H. This is the Fischer projection. What is this? This is a Fischer projection. Fischer projection for D3Os. Now, from this structure, we can write this way. The other way of representation is how we can represent in the zigzag manner. CHO, this carbon, this CH2OH. Okay, then this is the CH2OH. This hydroxy OH, yes, it is above the plane. Then this hydroxy, this side, yes, or the same way, this can be represented CHO, CH2OH here, OH. So these are the zigzag structures of D3Os. These are the zigzag structures of D3Os. Now, after knowing the zigzag structures and these things, we are moving to the great concept, that is a mutarotation. So I am just explaining about the mutarotation over here. There are some more conformations are there we are going to study in the next lecture. But before that, we should understand the little concept. If you find more literature or something like that, you can go ahead. Mutarotation. So mutarotation, what is the condition for mutarotation? For the mutarotation, your compound should be crystalline. Optically active, and it shows a time-dependent change of optical rotation. What is their requirement? Compound should be crystalline in nature. First thing. Second thing, it should be optically active, and you have to take in the solution form. Means you have to use solvent. That solvent may be water or any organic or any solvent. So what definition comes? Your crystalline compound should have an optical activity when dissolved in a solution. It shows a change in its optical rotation. So what will show it? Change in optical rotation. To reach the equilibrium. For what? To reach the equilibrium in the rotation. So that rotation is called as mutarotation. So this is about today's lecture. In the next lecture, we will study some more conformations like projections, like Newman projections, and some part of Fisher projection, whatever is remaining, that also we will consider Newman or and thank you for watching this video.